I think by now probably we just have everybody now here. So guys, I mean, it is my great pleasure to have Boumediene Hamzi with us. I have known Boumediene maybe for half a year or something. Boumediene maybe a bit longer,
Yeah,
and
maybe 1 year, yes.
he is doing, I think, a very deep and exceptional work in the field that is not that popular now, but should be. And he's trying to merge the fields of dynamical systems with the field of machine learning, but in a non-trivial way. In particular, he's interested in analyzing and formulating uh, dynamical systems in what we call feature spaces. That's related to kernel machines in machine learning. I think that's a great idea. So I'm very much looking forward to what Boumediene will tell us. I think Boumediene, you are a Marie Curie Skłodowska Fellow, right? At
Yes,
Imperial.
yes, yeah.
You're right. So this talk is going to be recorded. So if you have any objections, I think um, you just need to be aware of this. And with regards to questions, I suggest that you just put questions in the chat box, but I'm going to concentrate on Boumediene's talk. So unless it's really, really urgent, I would like to ask you to ask questions after Boumediene finishes his talk.
Yeah.
Okay.
All right.
And
Perfect.
so Boumediene, the stage is yours.
Okay. Thank you very much for the introduction. Yeah. So today I'm going to give a summary of some work that I've been doing for about the last 10 years on the intersection of machine learning and dynamical systems. And so it's a joint work with many people. And then the goal here is to show that there is a interaction or intersection of machine learning and dynamical systems in a particular kind of Hilbert spaces, which are called reproducing Kernel Hilbert spaces. So as Peter mentioned, I mean, the goal is to combine between the theories of dynamical systems and machine learning. And then the goal here is to propose a database, the qualitative theory of dynamical systems for analysis, prediction of nonlinear systems, as well as control. Yeah, so, and the approach is to view producing Kernel Hilbert spaces as linearizing spaces. And by linearization, we mean that we'll be embedding nonlinear systems in a particular kind of Hilbert spaces, which are called reproducing Kernel Hilbert spaces, where linear system theory will be applied. And the main motivation is that working in reproducing Kernel Hilbert spaces allows to find a nonlinear version of algorithms that can be expressed in terms of linear products. So, and the outline is as follows. So I'll start talking about function approximation in reproducing Kernel Hilbert spaces. Then I'll be talking about probability measures in RKHS, as well as the maximum mean discrepancy, which is a metric between probability measures. Then I will talk about one of the fundamental problems in kernel methods, which is the problem of kernel selections. And then so I'll be talking about kernel flows for learning chaotic dynamical systems. Then I will talk about detection of critical transitions for some slow fast SDEs. Then I will talk about nonlinear control systems in reproducing Kernel Hilbert spaces, and then how they can be approximated using tools from linear control theory. And same thing will be for Stochastic solutions of the Fokker-Planck equation of some nonlinear SDEs. Then we'll talk about construction of Lyapunov functions in reproducing Kernel Hilbert spaces. Then finally, we'll talk about approximation of center manifolds, as well as a database theorem for center manifolds. Yeah, so the summary of the approach is that we assume that there is a mapping from Rn into H, where H is a reproducing Kernel Hilbert space. And then we perform an analysis in general, but not necessarily a linear analysis in H. And the goal there is to simplify the computations and the analysis in general, and then get some conclusion there, and then come back to Rn. So the embedding or the transformation phi is obtained from the kernel that defines the RKHS. So in general, it's not necessary to explicitly find the phi, and then in practice, we'll be using the canonical feature map that is defined as follows. So phi ix is equal to kx x of ti. So k is a function of two variables. So one of the variables will be will be the measurements. So in here, I mean, essentially the measurements will be used to construct a Hilbert space where computations become simpler. And yeah, people who are familiar with quantum mechanics, I mean, they already see a flavor of quantum mechanics here, because there means, yeah, you construct a Hilbert space from the data, and then you analyze the system there, and then you come back with conclusion about the system. So yes, I see some I mean, there's some connection there, I mean, at least philosophically speaking. Okay, so what are they? I mean, they are these reproducing Kernel Hilbert spaces. Before anything else, they are Hilbert spaces that appeared in the 30s as an answer to the question, when is it possible to embed the metric space into Hilbert space? So you already see here that metric spaces are encoding nonlinearities, and then people in the 30s, because the computational power was not that high, were interested in performing linear computations by flattening the space, and so moving into Hilbert space. And then the answer was that if the metric satisfies certain conditions, it is possible to embed a metric space into special kind of Hilbert spaces, which are called reproducing Kernel Hilbert spaces. And then there was have been a lot of work on this this kind of spaces in the 50s through the work of Aronjan, and then Schwartz in the 60s and later on. Yeah. Yeah, so what are they? I mean, they are Hilbert spaces before anything else, with two extra properties. First one is the reproducing property, which is the property I here, that reminds us of the property of the Dirac function. But yeah, the Dirac function doesn't really, is not a proper reproducing kernel for technical reasons. But at least we have this reproducing property in the sense that the evaluation functional here, so if you want to evaluate a function at a point, you just take the inner product of f with the kernel. And the second property is that the closure of the span is dense in H. So in other words, reproducing kernel is reproducing kernel Hilbert space is a Hilbert space with a reproducing kernel whose span is dense in H. And then equivalently here, an RKHS is a Hilbert space of a function where all evaluation functionals are bounded and linear, and this is where the Dirac function fails, because it's not a bounded evaluation functional. So important properties of reproducing kernels are that the RKHS is unique. So the feature map doesn't have to be, the feature map doesn't have to be unique, but the RKHS is unique. We have symmetry, we have positive definiteness, and then we also have this property, the last one, that kxy writes as the inner product of kx dot with ky dot in H. And you see, this is exactly what we were looking for from the beginning, which is embedding the metric space into a Hilbert space. So we are able, we essentially want to write down kxy as the inner product of two objects in H. And this is what leads immediately to the canonical feature map, which is phi cx is equal to kx dot, and then it's coming from this property here. Mercer kernel is a continuous positive definite kernel, so it just add an extra assumption of continuity on the kernel. And the fact that Mercer kernels are positive, definite, and symmetric reminds us of similar properties of Gramians and covariance matrices. And this is something that we'll be using a lot in this work. Examples of kernels are monomials, Gaussians, and hyperbolic tangent. So yeah, we'll be using some of this in the computations. Another way to find the embeddings from the kernel is by considering the integral operator associated to the kernel that is defined by the following integral operator. Then one looks at the eigenvalues and the eigenfunctions of this integral operator, and then we see that this is kxx prime will write according to what we are interested in. So that's Mercer theorem. So since k is positive definite, the lambda j's will be positive definite, and so we can write down the lambda j's in this decomposition as the square root of lambda j times cj of x times square root of lambda j cj of x prime. And this is exactly what's going to give us the Mercer embedding, which is defined by the square root of lambda I psi of x. So that's one way. That's another way actually of finding the embedding. So phi is not unique and depends on the measure. and in general it's difficult to compute. But as I mentioned before, I mean, one doesn't have to go through that way, and one can use the canonical feature map. So it's not necessary to invoke Mercer theorem just for discussing the feature maps. And these are like just examples of how to compute non-Mercer feature maps using the canonical feature map. So for a polynomial kernel, for example, one could just expand this in a product, and then one will get the embedding just through direct computation. And same thing for the Gaussian kernel, one could get immediately the expression of the embedding through just the expansion. So Mercer theorem is, however, fundamental to find error estimates and study the smoothing properties of kernels. But as I mentioned, I will not be talking about this theoretical work in this presentation. So RKHS play a role, important role in approximation theory, where the goal is to learn a function, an unknown function f from random samples, and so the usual way is to minimize the least square error given by the integral of f of x minus y square 0. So one could minimize this error, and one will get the regression function defined by the following integral. But in general, I mean, we don't know rho, so one has to discretize this criterion, and then we also add the regularization parameter to get a solution for this minimization problem. And yeah, so here the regularization term will be in the RKHS. So the minimization is taken over functions from a hypothesis space, often taken to be a ball in the RKHS HK associated to the reproducing kernel, and we get an easy closed expression of this function. It's the sum of Cj kxxj, and then if you remember, I mean, this is exactly the canonical feature map, which means that fs of x will be written as can be written as the sum of Cj phi of x, which is we could already see here that this is like linear in phi j. So one of the nice features here is that one could write f of x as a linear combination of this variables phi j of x in the RKHS. And the CJs themselves, I mean, they do satisfy a system of linear equations that are given by the following set of equations here. And so we call learning the process of approximating the unknown function f from random samples on Z. Another thing that we'll be using in this work is the empirical kernel matrix, whose entries are kxi xj. The restriction operator, which is defined as the follows. So you take a function, and then the Rx applied to f is fxi for I varying from 1 to m. And then the adjoint of the restriction operator, which is given by the following expression. Another application of RKHS is the RKHS in the change point detection, where we are interested in the sequence of samples x1 to xn from a domain X. And then one is interested in detecting a possible change point tau, such that before tau, the samples xi follow probability distribution p, and then which is the background distribution. And after the change point, the samples follow the probability distribution q, and one wants to find that change point. So here, where the approach that will be adopted is to map the data set in RKHS and then compute a measure of discrepancy. And delta n will be small if p is equal to q, and large if p and q are far apart. And we'll be using the metric, which is called the maximum discrepancy, that was introduced by Gretton in late 2000, which is essentially the difference between the kernel mean embeddings of the probability measure. And this is what we'll be using as a measure of heterogeneity. So yeah, so what happens here is that we take probability measure, and then we embed it into an RKHS by considering its kernel mean embedding that is defined by the following integral. And then the MMD between two probability metrics, between two probability measures, is defined as the following distance between two such mapping in the RKHS. So this, this can be defined explicitly in terms of the kernel. So one doesn't have to go into a feature space. So it is a pseudometric because it doesn't satisfy all the conditions. So it satisfies almost all the conditions, except that the fact that it's 0 doesn't imply that it is that P and Q is equal. P and Q are equal. So for it to be a metric, it is sufficient that the kernel is characteristic. That is that the mapping from P to H is injective. And this is satisfied by the Gaussian kernel, for example, on compact domains or on RD. So that's an illustration of what happens. For example, in this setting, you have two probability measures P and Q. So one maps them into their RKHS and then computes the distance between their means, and then one gets this metric. And then here, for example, you have this two probabilities, red and blue. And so this MMD is maximal when the two probabilities are far apart. And yeah, one interesting result is that this probability metric is guarantees that we have convergence in distribution if and only if we have convergence in MMD. And one of the advantages that is it can be computed directly from data without having to estimate the density as an intermediate step, as many of other metrics. And then we'll be using this expression here, where given two samples, x1 to x, m from P, and y1 to y, m from Q, and unbiased estimate of the MMD is directly obtained through this expression. Yeah, so so now we are going to look at the question of how to choose the kernel. So yeah, so there's this method of kernel flows that was introduced last year by Human Ohadi from Caltech. So given an input-output data x1, y1 to x and yn, and then we are interested in recovering an unknown function u star from random samples. So in the setting of optimal recovery, the problem that we saw before was ill-posed. I mean, this is where the regularization came in, but it can be turned into well-posed problem by restricting candidates for U to belong to a Banach space. Yeah, with a certain norm that I didn't write here. And then identifying the optimal recovery as the minimizer of the relative error that is given by the following the following problem. So the minimization over V and then followed by maximization over U. So here the unknown function is U, and then V is the approximant. So max is taken over U, and then the mean is taken over candidates in V in the same Banach space, such that Vxi is equal to Uxi is equal to Yi. And so the method of kernel flows is based on the premise that kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. And so this led to the introduction of that rho that we talked about, which is the norm of V star minus Vs square over norm of V star square. So where V star is the true function, and then Vs is the random sample. Yeah. And this can be expressed directly using this form of the represented theorem, which is given here. And then, so what happens now is that if one has a family of kernels, k theta x prime that are parameterized by theta. So here I will be talking about the parametric version of kernel flows. There's a non-parametric version which is about deforming the space, but I'll not be talking about it here. So the kernel flow algorithm in this setting is that we select. So we have a data set. So first we start with the subsample, and then we take a subsample, and then we compute the rho. So YC is the subsample, and then YF is the subsample, and then K theta is the kernel covariance matrix for the subsample and subsample. And then we perform gradient descent over rho, and then update the parameters of the kernel according to that algorithm, and then repeat until we get convergence. So so now we apply this to the context of dynamics. So I'll assume that we have time series x1 to xk, and then our goal is to forecast xn plus 1 from observations x1 to xn. So we work on the assumption that this time series can be approximated by a solution of dynamical system of the form zk plus 1 is equal to f dagger zk to zk minus tau dagger plus 1. So f dagger may be n now. So yeah, so what we want to do is just essentially apply the problem of approximating an unknown function from random samples, but we'll be using Kernel flows, I mean, and then see what happens. So given or producing Kernel Hilbert space of candidates for f dagger, and then using the relative error in the RKHS norm that we introduced earlier, which is the raw function, the interponent admits the following representation, but then we'll be using a regularization here for the to allow for inversion. And then in the dynamic context, I mean, we are going to also use different variants of Kernel flows. So here, so we see mostly like Kernel flows as a philosophy instead of just a method on its own. So the first variant of Kernel flows is the one that was introduced by Human last year. But then we can also think about metric associated to Lyapunov exponents. And the premise is that the kernel is good if the estimate of the Lyapunov exponent obtained from the kernel approximation of the dynamics does not change if half of the data is used. So we use this rho L lambda max n minus lambda max n over 2. But also, I mean, this can be modified as suggested by Lyudmila about, I think 2 or 3 weeks ago in this school in Pisa. So we can also think about all the Lyapunov exponents. So it doesn't have to be only the maximal Lyapunov exponent, but it could be a rho L where we are interested in minimizing a rho associated to all Lyapunov exponents. And then third one would be a metric associated to the MMD. And yeah, so this would be a minimized rho MMD given by the MMD between S1 and S2, which are 2 different samples of the time series. Or you can take one sample and then one subsample and then run the method on it. Yeah. So we'll be using this, using this kernel. I mean here with the 10 parameters. Yeah. So and then the goal is to learn these parameters from the time series. Yeah. Yeah. So you apply it for the Bernoulli map. And then we see here that yeah. So we are comparing between cases where the initial kernel remains the same. There is no learning of the kernel, and then so here, so this is the figure with the red and the blue. So this is without learning the kernel, and then with learning the kernel, it's the one on the left. So it's almost identical. And then we have also this one here, where the blue is the true trajectory. The red is with the kernel after learning, and the green is for the kernel without learning. So that's one thing. And another thing is about the Lorentz system. So we apply the same kernel, and then we predict the dynamics for the 3 states, and that also gives interesting results. So this is for the short term, but also interestingly, here that there is also here this like different rows and different components. Yes, again, we apply the 3 different rows. The one corresponding to the RKHS norm, the other one for the maximal Lyapunov exponent, and the other one with the MMD. And then so here these are like an approximation of the attractors. So you see that for the first, third, and the 5th figure, we are having an approximation of the attractor with learning the kernel, and then the 2nd, 4th, and 6th. So it's after learning the kernel, which you see. So one sees improvement in the approximation of the long-term behavior. So here, again, it's not only about approximating or making prediction of time series. We also are interested in qualitative theory of dynamics. So we are interested in also long-term behavior. And that's the reconstruction of the attractor in 3D. So we see improvement in the estimation through learning the kernel. And recently in the last, I think 2 or 3 months, so we also started working on prediction of climate data that was provided to us by Ramit Malik from the Argonne National Laboratory. So here we see, I mean, there is an example of temperature prediction. I think it was in Chicago. And then we see, I mean, that we have the true data is the red one that is directly provided by satellite. And then the two other ones are are provided by different methods to solve the PDEs exactly. And then the blue one is through kernel flows that we did run on my just personal laptop. And then we see that essentially we are performing, having good performance. This is for temperature prediction. And then also for applications for the entire profile, I mean, we also got some data sets. So Romit was able to get this for the entire profile. And then you see we are comparing between, true data set, kernel flows, PDE based short term, and then PDE based long term. And so it seems, I mean, that it's doing all right. I mean, there's probably room for improvement, especially for this vertices in green here. So so we are working on this kind of improvement. But so it's probably so far. So for this, we used a kernel with 30 parameters, where we used the triangular kernel, locally periodic kernel, and then polynomial, and then many other ones. So we just combined between all of them, and then we did run kernel flows. Yeah, I think it would be interesting to see how this compares to Juan Pablo's results, and then all the other work on reservoir computing. So I'm still not clear totally what are the links, but I guess that there are probably links between reservoir computers and kernel flows. Another application is the detection of critical transitions for multi-scale systems. So we looked only at this particular kind of SDEs, where it's slow fast system, and then we were able to show that for this kind of particular class of system, the MMD allows to detect critical transition, and then it's maximal at the critical points. So here I'm just going to go quickly through this, because I don't think I have a lot of time. So we look at the stochastic van der Pol case, and then which has some critical points here, which are like periodic, and then we show that the MMD is maximal at this critical point. So what remains to be proven here is whether we can extract an early warning signal or not. So that's still not clear yet. But yeah, so maybe with kernel flows that can be done. So another application is to look at the approximation of control systems in RKHS. So for this work and the next one about, and then the other one about SDEs. So we want to look at, we are interested in looking at linear theory as a paradigm for nonlinear systems. So we want to use linear theory and apply it directly in the RKHS to a nonlinear system that is being embedded into an RKHS. So in the case of context of nonlinear control systems, we are going to look at balancing. So we consider a linear control system x dot is equal to ax plus bu, and y is equal to cx, where a, b is controllable and ac is observable. And then a has eigenvalues on the left open half plane. So we define controllability and observability Gramians as the following objects, WC and WO. And these two matrices can be viewed as a measure of the controllability and the observability of the system. So essentially, they are directly related to the following energies. So LC is defined as the minimal energy required to reach x naught from 0 in infinite time, so which is defined by the following integral. And then we define LO as the future energy, which is defined as the output energy regenerated by releasing the system from its initial state x naught and then 0 input. So that's LO. So from linear control theory, so this LC and LO may have a closed expression that is given by the following expression, which is LC is half of x0 transpose WC minus 1 x0, and LO is half of x0 transpose WO x naught, with WC and WO satisfying the following Lyapunov equations. So here the observation is that LC and LO, they can be written in terms of inner product, and then the goal is to approximate this similar objects for nonlinear systems using this observation that LC and LO can be written in terms of inner products, and so one will map the solutions of the nonlinear system in Rn into H through an embedding, and then we would try to see if there is a way to get this similar observations for the nonlinear system. So these grammars, I mean WC and LO and WO, have been used a lot in the linear control theory, and then specifically for the purpose of model reduction. And the goal here in the method of balancing is to find a representation where the system's observable and controllable subspaces are aligned, so that reduction, if possible, consists of eliminating uncontrollable states which are also the least observable. So one is interested in looking at the input-output behavior of the control system, and then the claim is that the states that are hard to reach, i.e. the ones that require a lot of energy from the input, so when LC is large, and then that do not generate a lot of energy at the output, so i.e. the LO is small, then these states are not important, and so one could discard them. So one is interested in finding a coordinate system where the measures of controllability and observability, the WC and WO, are aligned, so they are equal, and then we get this will be equal to some matrix sigma, and so the entries of this sigma, once diagonalized, will give us a clear understanding of the input-output behavior, and then one would look for a spectral gap and then eliminate the states where sigma k to sigma n are small. So we are interested in finding a T such that TWC T transpose, so which is the T is the transformation, the balancing transformation, is equal to T minus T WO T minus 1 is equal to sigma. So once we get this, then balancing becomes an easy task, between quotes. And so we are looking for a K such that sigma K is much greater than sigma K plus 1. And then if we get this, then xk plus 1 to xn will be assumed to make a negligible contribution. And to find such a T, there are many methods, but the easiest way is to look at the Cholesky decomposition of WO, get a matrix Z, and then perform an SVD of Z transpose WCZ, and from there get this transformation. So our goal will be to look for generalization of this into for linear systems, and this is what we did in this work. Yeah, for nonlinear systems, I mean, as I mentioned, there have been some work, especially due to Sharpen, where she looked at nonlinear systems of the following form, so which are affine in the input, and she proved that so the LC and LO satisfy two equations. The LO is the Lyapunov equation, and LC is the Hamilton-Jacobi-Bellman equation. And so these two PDEs are not that easy to solve. There have been a lot of work trying to find approximate solutions for them. And then she proved also that there is a balancing transformation under certain conditions. So one could diagonalize both solutions and end up having a balancing transformation. So as I mentioned, there have been a lot of work trying to solve these two PDEs and then compute the coordinate x equal to phi of z, but there's no systematic method. So there have been some methods based on Taylor series expansion or using statistical approximation, where the system is excited with white Gaussian noise and then computing a balancing transformation using an algorithm from differential topology. There have been some essentially linear empirical work when one looks at the linear approximation. So what we want to do is, as I said, we want to use linear theory of the nonlinear control system in the RKHS, and then you apply linear balancing in the RKHS, and then get an approximation of the original nonlinear system. So so in linear case, as we saw before, there is a way to find an analytic solution by solving two Lyapunov equations. There is a database approach where one excites the system with impulses from the input and then impulses from the initial condition. So one will come up with two covariance matrices, and then when one will get one will diagonalize them and then perform get a balancing transformation. So that's just a way of discretizing the integral, and that is exactly what we are going to do in the RKHS, except that these objects, I mean, instead of being covariance matrices, will end up being covariance operator, because we'll be working essentially in an RKHS, which is infinite dimensional. So this is what I was mentioning before, is that how to compute probability and observability energies from data, and then how to extend this previous approach to nonlinear control systems. And so this is what will be done through feature maps. So what we do is we consider a nonlinear control system of the form x dot is equal to fxu and y is equal to h of x. So as I mentioned before, LC x naught is equal to half of x0 transpose wc minus 1 x0 can be rewritten as the following inner product. So it's WC pseudo inverse x naught with x naught, and with times 1/2, and then LO, which is half of x0 transpose WO x naught, can be written as the inner product of half of inner product WO x0 with x0. So essentially, we are tempted by saying that, since this is like an inner product, and using the kernel trick, LC can be written as WC pseudo inverse H with H, and LO with B WOH with H. With H is the embedding. However, I mean, there are some complications because we'll be working in some infinite dimensional space. So and then essentially about this operator that is here, and the same one, the W sub pseudo inverse and the WO. So questions of invertibility and and being and domain of definition. So so we could show using this operator that we talked about before, the restriction operator and its adjoint, that we have a closed expression for LC hat, which is given by the following form, and similarly we have a closed expression for LO hat, using this kind of computations and kernel trick, and then using this restriction operator and this adjoint. So one could get a closed expression for the solutions of at least an approximation of the LC and L hat using the kernel LC and LO hat using this kernel trick. So the approach is as follows. I mean, we consider a nonlinear system of the form x dot is equal to fxu and y is equal to h of x. So we assume that you can apply the method of linear balancing when the system is lifted to high, possibly infinite dimensional feature space, carry out linear balancing and truncation using exactly the same approach in the case of linear balancing, and then we discard an important state, and then construct a nonlinear reduced order model by learning approximations to FH defined directly on the reduced state space. So here, as I mentioned before, the Gramian, the empirical Gramian in Rn becomes the following expression, which the X will be mapped into the RKHS, so this becomes a covariance operator. So that's an example of what we will get in H. But again, luckily, we don't have to go into that route. I mean, you could just compute the kernel covariance matrices in the RKHS and then perform linear balancing, like being done in the linear case. So that's exactly what we do here. So we compute KC and KO, perform an SVD, and then compute the balancing transformation into the RKHS, and then look for a spectral gap, and then from there we're going to get an approximation of the nonlinear system using this approach. So that's just an academic example. We have like 7-dimensional system. So we excite it with the impulses from the input and the initial condition. We construct the kernel covariance matrices, and then we do balancing. Yeah, so here, this is like the how which kind of input we use for testing, which is sum of sine and this square matrix, square input. So we can compute these kernel covariance matrices. Here, so we look at the first 100 singular values, which is the red one here. I mean, there's another example in 2D, but here I'm just going to talk about the 7D example. And we see that there is a spectral gap between the second and the third one of order 100. So the first one and second one are of the same order. So yeah, so we are going to assume that see that the system is going to be model reducible to dimension 2, and that's what we see. This is what we check in the simulation. So we have this control input. So the original output is the blue one, and the reduced is the red one. And you see that they are close to each other. Other application is SDEs in RKHS. So here we adopt again the same philosophy. We are interested in seeing if there is a way to use linear theory as a paradigm to estimate quantities for nonlinear SDEs once mapped into an RKHS. So what we are going to look at is the SDEs that are excited with a wide Gaussian noise. So here we have a control input. We have control system. We're excited with wide Gaussian noise, and then we want to look at the stationary solution of the Fokker-Planck equation that is given by the following object. And we are going to use the linear estimate as a basis to estimate the nonlinear object. So for linear systems that are excited with wide Gaussian noise, I mean, we know that it's sufficient to find the mean and the covariance of the solution xt in order to uniquely determine the transition probability density. And we can also express the mean. So here is if A is stable, so the mean will be 0. The covariance satisfies the Lyapunov equation for WC that we saw before, which is AQ plus QA transpose equal to minus BB transpose, and which is exactly the WC. And so essentially, I mean, one gets that the steady state probability density for the linear setting is rho infinity is proportional to exponential minus LC. So this is minus exponential minus half X transpose WC minus 1X. And then this is exactly what we had for LC. And so what we want to see is whether this is going to be useful for some other nonlinear SDEs as an estimate. So as I said, I mean, even though this estimate here, rho infinity hat is being proportional to exponential minus LC hat, is valid only for a small class of systems, linear and some Hamiltonian systems. So what we want to see is, if mapping a nonlinear system into a suitable RKHS, is it possible to extend this connection to a larger class of nonlinear systems? So so what are the assumptions? Is that we assume that we have this SDE that is here, and then we assume that there is a phi that maps the solution of this SDE into an OU process in the Hilbert space. That's the first assumption. Yeah, so characterizing the class of SDEs for which this is possible, I'm still so there is an open question. So I'm not totally clear under which conditions this assumption is possible. But it seems to be reasonable for some SDEs, as we'll see in an example that I'm going to show in a moment. Second one is that the measure P infinity, that is the invariant measure of the OU process is the push forward along phi of the unknown invariant measure. So since we know that the OU process, we know what is the P infinity for the OU process in H. I mean, the goal is to see if we can get this back for the original nonlinear SDE in Rn. And then we also assume that mu infinity admits a density. Yeah, and then we, as I said, that's the main, so that's the main estimate that we are having here. So we proved some results for like statistical results, like a consistency results for these estimates in the paper. So here, what I'm going to just show is the numerical experiment. So so we have this double well potential where we have two bumps, and then you see that by numerically estimating it is the black one, and then the green one is through the RKHS estimate using the one I mentioned before. So even though it has two bumps, I mean, it could have been. I mean, we were able to recover it using the fact that we could using the linear estimate for the OU process in H. So another application is the construction of Lyapunov functions from data. So here we are interested in the following problem: is that given nonlinear ODE x dot is equal to f of x, to assume that we don't know f, but we have x of ti's. We'll approximate f from x of ti's. We find the Lyapunov function v hat for f hat, and then we prove that v hat is also the Lyapunov function for f. That's the strategy here. And as you may know, Lyapunov functions are important in nonlinear system theory because they allow, for example, to prove stability, but they also allow to estimate the Bayesian of attraction directly from the Lyapunov function. So this would be the assumption here, that we assume that the zero is an equilibrium point, that it is exponentially asymptotically stable, and then one could estimate the Bayesian of attraction from the level sets of the Lyapunov function. So what is the Lyapunov function? It's it's positive definite function such that its orbital derivative defined by the following object. So the inner product of the gradient of V with f is strictly negative. So it can be less or equal to 0, but then one has to use the Lassalle's invariance theorem to prove stability. And then, as I mentioned, I mean, one could look at level sets of the Lyapunov function to get domains of attraction. So one of the ways of constructing a Lyapunov function is to solve this kind of differential, this kind of PDEs. So remember the main condition on the Lyapunov function is that its orbital derivative is negative, which is like a differential inequality. But one could look also at some PDEs where one fixes the right-hand side. For example, here a norm of x minus norm of x squared, but this has been extended to some classes of functions where the right-hand side is some function that satisfies certain conditions, and as we'll see in a moment, and then one solves term by term this PDE. So that's the idea of Peter Giesel, where he proposed an algorithm to approximate Lyapunov functions using radial basis functions. So it's based on finding an approximate solution of this linear PDE, and in general with as I said, it's either minus norm of x squared, which is the most popular choice, but sometimes it's better to use the other kinds of p's. And so what he showed, that if the p satisfies the following condition, that it's positive, then it's of this order eta, and then as well at this following condition, then there exists Lyapunov function such that LV1 is equal to minus p of x for all x in the Bayesian of attraction of x naught, which is the equilibrium point. So how this this algorithm works? It works on a similar premise that one can use linear theory in the RKHS. So here the RKHS is spanned by a Wendland function, so the kernel is fixed. And so the only difference here is that this is like a generalized interpolation problem where the coefficients become differentiation, so it becomes a differential operator. So here you see this, there is this extra term here, which is delta xk composed with L. So L denotes differentiation with respect to y, and then followed by evaluation at y is equal to xk. So so before so remember, like we had this problem of approximating an unknown function from random sample. So here the coefficients become will involve the differentiation in them. But still, I mean, you see the structure is still linear, and then to find this coefficient, one uses one could solve this system of linear equations again for the coefficients, and then get the solution of an approximation of the solution of the PDE. And then this is a proof that Giesel introduced, which with Wendland, which to show that the Lyapunov function, which is an approximation of the solution of the PDE, is also a Lyapunov function for the original system. So what we want to do is, is to generalize this work to the case where f is not known, and then we assume that we have unknown samples x, I, y, I. So from the dynamical system, and then we want to find the Lyapunov function based on this kind of assumption that we don't know the right-hand side of the ODE, but we know the data from it. So and then we proved actually that this is possible. So we by finding a good approximation of the f, we could show that we could find the Lyapunov function for the approximated dynamical system, and then this Lyapunov function itself is an approximation of the Lyapunov function of the original system. And this is just an example where we now the Lyapunov function here just a quadratic function, and so we see that this is the numerical experiment showing the Lyapunov function with when we increase the number of points. So here it's 360, and then we have 1,000 points, and then we see that the orbital derivative is decreasing by the number of points. So here we had like some sharp edges, but then by increasing the number of points, we get negative definiteness of the orbital derivative. So last part is about center manifold approximation. So that
I we would like to have few minutes at least for questions.
Okay.
I think some people will have to leave on an hour.
Okay. Sorry. So I'll be finishing quickly here. So I'm almost done. Okay. So here we So I'll just go to quickly about this. So we have a center manifold theorem where we are interested in analyzing the stability of this equilibrium point, where we have some eigenvalues on the imaginary axis and other ones on the left open half plane. We use the center manifold theorem to show that the stability properties of the full order system depend actually on the reduced order system whose linear part is on the imaginary axis. So that's the center manifold theorem, and this center manifold satisfies this PDE, which is given here. And then what we did is to solve this PDE using kernel methods, and we also got a kernelized version of the center manifold theorem that shows that we are able to prove stability of the full order system from the stability of the reduced order system on the approximation of the center manifold theorem by using the solution that we got of the PDE that defines the center manifold. That's the theta. So by getting approximation of the theta from the data, we get an approximation of the dynamics, and then by studying its stability properties, we get the same stability properties of the full order system. So that's an example where we illustrate these kind of things. I mean, we have x dot is equal to xy, whether they have one eigenvalue on the imaginary axis and another one here. It's this is like a negative. And so by looking at two different kernels, here analytically one can find the center manifold. And then by looking at two different kernels, we show that we effectively have an approximation of the center manifold. Yeah, okay, and that's it. Yeah, so to conclude, we used we used Kernel flows to approximate chaotic dynamical systems. So we also showed that the maximum discrepancy can be used to detect critical transitions. So we introduced estimators for the contrariety and observability energies that were used to model for model approximation of nonlinear control systems. And these were also used to estimate the stationary solution of the Fokker-Planck equation governing some nonlinear SDEs using linear estimates. And so this, results show that RKHS do act as a linearizing space. So we also introduced a database approach for the construction of Lyapunov functions, a center manifold approximation, and the database version of the center manifold theorem. And so these results collectively argue that working in reproducing Kernel-Hilbert spaces offers tools for database theory of nonlinear dynamical systems. And yeah, that's it. I mean, that's the take-home message. And these are like some list of references. Yeah, and that's it. Yeah, thank you for your attention. Yeah.
Okay, thank you. Thank you, Boumediene. So we.
Yeah, so sorry for going over time. I didn't realize actually that.
Yeah, so we, sorry. So we don't really have time for many questions, but you know, if people would like to ask questions, please do. You can unmute yourself and just ask directly, or you can just put it in the chat, but whatever is good.
I will have a question if possible.
Gabriel, yeah, sure.
Hi, Boumediene. So thank you for the nice talk. So I have a question, two questions actually on the kernel flows. So one is, I get the philosophical idea of leaving out half of the point and training the kernel on half of them. But is there a particular reason for using half the point or not? So do you ever investigated other techniques to leave out something else? And
yes. So half of the point. Yeah, let me just answer one by one, so that I may forget the first question. Yes. So half of the point. I mean, there isn't actually, because the original paper they talked about half of the point, but then I tried actually to have like just a random variable between 0 and 1, and this worked quite well. So I think the half of the point is just like say that you are using a random subsample. Yeah, but
so
half
is special about.
There is nothing special about it as far as I understand. Yeah.
And the other point in the experiment that you show, that it looks really like the kernel that you learn by that kernel flow is much better in predicting the behavior of the system. But my question is, if the evolution that you have shown is the same that you use for training. So do you learn a kernel that is really good also to predict your dynamical system outside of the training data, or the experiment that you have shown is only showing the error on the training data? So how good is to generalize, let's say?
So here we use this for testing points, right? I mean, it's not for the training points. So the results I was showing were for different initial conditions.
Okay,
fine. But of course, I mean, all right. I mean, here like sorry, I need to charge my my battery is dying. So as I said, I mean, it's so it's good to have like an estimate for different initial conditions. Then actually, I started like looking at this analytically speaking by using similar arguments as Ed Ott's paper, where you could compute the Lyapunov exponents between an original system and an approximation using kernels. But I think there's probably a way to characterize this uncertainty, using Lyapunov exponents. But other option is also to look at this kind of arguments that Juan Pablo and Ludmilla used in their work on reservoir computing to show learnability and then approximatability, but I still don't know all the details about their work. So I think it would be nice to see this.
Thank you for the answer.
Yeah.
So we have a question from Gosia Kowalska. How Hilbert kernel approach compares to other linearization decomposition methods, for example, Koopman operator methods?
Yeah, that's a good question. Yeah, so I think, I think philosophically there is a difference in the sense that here we don't assume that the dynamics of the observables is linear, right? I mean, this is what I mentioned at the beginning, that the goal is to apply linear theory in the RKHS. So we don't assume that the system is linear in the RKHS. So it could be possible that the system in the RKHS, whether a dynamical system like autonomous or control or random dynamical system, it could be that it is linear, but it doesn't have to. So it could be that it's non-linear, but the goal is to apply linear theory to it. So that's, I think, what I see as a philosophical difference. But I see definitely, you are right. I mean, I see definitely the point, and there's probably a link there, which needs to be explored. But I see that there is a slight difference in the approaches. That one is assuming linear dynamics in the higher dimensional space, and the other one is assuming that the linear theory applies there. So it could be that the system is linear or not linear, but you apply linear theory to it. Yeah.
Right. Andrew Flynn, is it possible to find a single kernel that can produce the dynamics of two different chaotic attractors?
It's possible to find a single kernel that can produce the dynamics of two different chaotic. Yeah, yeah, that's a it could be. I don't know exactly. Yeah, that's a good question. Yeah, but it depends on what you mean, right? I mean, so here I have you mean like one kernel that approximates two dynamical systems, or in the long run, or
Hi, Boumediene. So what I'm asking is, so I'm coming from the reservoir computer side, and what I'm interested in is multifunctionality. So a single network that can perform two different tasks. So say, for instance, you find a kernel that can reproduce the dynamics of the Lorentz attractor, find a kernel that can reproduce the dynamics of the Rossler attractor. Could you find a single kernel that could do both?
Yeah, but you probably have to retrain, right?
So what I do with my reservoir is I have training data for both, and I'm able to have a single readout matrix that can perform the dynamics of either attractor.
Oh, okay, yeah, that's a good question. Yeah, I don't know. As far as I see, but I could be wrong. I think that is not possible with this kind of approach, because you are learning one kernel and then you fix the parameters, and then you are able to get one dynamical system. But then if you want to get another dynamical system, you need to do another training. But to get both with one training, I mean, I doubt that this is possible. Yeah. So you are saying that with one training you get both? With
the reservoir, yes.
Yeah. Now here, I mean, as far as I see, I mean, I think that's not possible, because you are training for one dynamical system, and then if you want to do another dynamical system, then you just have to retrain, and then yeah, unless you are looking for a vector valued kernel, and then then the coefficients will be instead of having scalar valued kernel, you would get like a vector valued kernel, and then you will have like two, for example, two entries for each in front of each kernel, and then you train first component, for example, for the first attractor, and the second one of the second attractor. Okay. But with one single kernel, I mean, a scalar kernel, I doubt that it's possible. But if you want to go to vector value, then probably it's possible. Yeah, but
okay, thank you.
Giannis Boutsinas, how can the method predict the Bernoulli map? The trajectory depends heavily on the initial condition.
Yeah, but I think it's because, yeah, you're right. I mean, I had a lot of trouble actually to come up with the solution of this. I think it's because of the nature of the kernel. I mean, the kernel, it was triangular kernel, so it was like there was like some discontinuity in the kernel that was approximating the discontinuity. Yeah, but you are right. But also, I think it's probably also related to Gabriel's question, which is for which kind of initial conditions you are able to get this kind of approximation. Yeah, so that's different.
Sorry, the question is, was it one trajectory? Because if we get, so because the graph that you showed, there was some prediction, but I don't understand, was it one trajectory? Because if we get two initial conditions, they may have nothing in common, because it's just the binary expansion of, it's a binary shift, right? And then training on one could be nothing for the other. So I'm not sure how it can, I don't see how it can be trained.
I think it's just the kernel. I mean, just the kernel was sufficiently expressive. So that's it. Yeah, I think that's the only explanation I could have for this kind of example. Yeah. But I also, as I said, it's probably the initial conditions were close enough for this kind of things here.
Okay, so we'll need to finish very soon. So we have Jiming Duan. How big is your problem? Are the methods scalable to large scale problems? This probably has to do with the usual problem of kernel method.
Yeah.
Is there another question? Is there any advantage of max-min discrepancy over KL divergence?
Yeah, so yeah, some big data for kernels. I mean, it's an open. I think it's very common for kernel methods, as Peter knows. And then, yeah, he also I think works a lot on this as well. Yeah, so I think there are ways actually to solve this kind of problems. I think one have to look at different ways of doing SVDs and for kernel methods. Advantage of MMD over KL divergence. Yes, I think this is so this is what I had in mind when I mentioned that one could be expressed directly using the data. And while if you use KL divergence, you probably have to go to the intermediate step of computing estimating the probability from the data and then finding the KL divergence from the estimates. Yeah, I mean, this is what I see as main difference. Yeah, but they are doing essentially the same job, except that one is can be computed directly from data, and the other one requires an intermediate step. Yeah.
Right. Okay, thank you. So, right, really enjoyed that presentation. So it was a very lively discussion. I would just have a very, very quick short one. I didn't understand the invariant measure. So if you get the invariant measure in the feature space, how do you go back?
Yeah, so that's the thing is that we just used this estimate, right? I mean, so we forced the estimate, and then we didn't have to go back. So we just had this estimate.
Oh, I see. Okay.
Yeah. Yeah, so that's, I mean, it was mostly of forcing an estimate and see if it works. I mean, so it was the kernel trick. So no need to go back. It's in terms of the kernel itself. Yeah.
Right. Okay. Perfect. So I would like to thank Boumediene again for an exciting talk and very lively discussion at the end of the talk. And thank you all for attending the talk.